Okay, today I shall talk on the subject particle in one and three-dimensional potential box. Myself, Dr. Dibyaduti Pramanik. I am in physics department. Okay, so what topics we shall cover? Let's see. Schrodinger wave equation for particle in one-dimensional box. For one-dimensional box, what will be the wave function of a particle? The energy of the particle, the quantum mechanical probability density, how to normalize the wave function of the particle in one-dimensional box. And the next thing, we shall talk that Schrodinger equation and wave function for particle in three-dimensional box. Okay. So, for the three-dimensional box, particle in three-dimensional box, I shall cover the topic energy of the particle in three-dimensional box and how the degeneracy is coming for that box. I shall talk on that topic. Okay. Now, see, this is the one-dimensional box. Okay. Now, you see just this is the x-axis and this is the wall. Okay. This is the wall. Here, this is the pure example. That means the application of the Schrodinger equation. We know that at first I shall start with that we know that there are three types of the Schrodinger equation. One is the time dependent and one other is the time independent. Okay, now depending on the application, you have to use the Schrodinger equation. So this is the purely application of the Schrodinger equation. Okay, now what is the application? You see that this is our x-axis. Okay, and here we have started one wall, that is the potential wall, this and this. This wall has been started from x equals to 0 and here at x equals to L. Okay, now and how far that wall has been extended, that means the V is the, you see, V is the potential, okay, parameter. Okay, V here V tending to infinity here and here V tending to infinity, that means infinite wall. Okay, now you see now you see here we have taken that conditions that V tending to, that is V equals to infinity like this at x equals to 0 and here you see and x equals to L. Okay, and V is 0 here, that means the potential is 0 here. You see V is equal to 0 here, that means within the wave, that means in between x equals to 0 and x equals to L, that means V equals to 0 for 0 less than x less than L. That is my condition and that is my application where we must use the Schrodinger equation. Now, which type of Schrodinger equation you have to use? You see here V is independent of time. That means we must use the Schrodinger independent equation, time independent equation. Okay. Now see here time independent Schrodinger wave function between the potential wave. That means we must use the Schrodinger equation within this well, not just outside the well. Okay, so within this well. Okay, that means here this is the Schrodinger equation. That means we are using the time independent. That means minus h cut square by 2m del 2 psi x dx square is equals to e psi of x. That means this is the eigenvalue equation. You see, h psi is equals to e psi. Okay, and where psi, that is the wave function, okay, is purely the function of x. Okay, now you see h. What is h? H is the Hamiltonian. That means within that Hamiltonian, you must write the kinetic energy. Okay, because the potential energy is 0. You see, just see here, potential energy see, potential is equal to 0 within that well. So if you want to use the Schrodinger equation within the well, that means you have to take only kinetic energy. So this is the kinetic energy, minus IH cut del x, okay, minus IH cut del x. That is the kinetic energy. So p square by 2m, that is operated on psi of x, it is given as a e psi of x. Okay, so this is the thing. This is the thing, and here we are using this thing, you see, 2me by h cut square as k square. K square. Okay, so my equation turned as d2 psi of x dx square plus k square psi of x is equals to 0, where k is this. What is k? Now ask me what is k. K is the propagation parameter. That means k is equals to, that means this k is related with the E, that means the energy. Now see, acha, you know this is the differential equation. See, question number, equation number 3 is the differential equation. See, d2 psi of x dx square plus k square psi of x is equals to 0. It is similar like a simple harmonic motion. So what is the equation for the simple harmonic motion? You see, d2 x dt square plus omega naught square x is equals to 0. You see, this is similar as this. Okay, so what will be the solution of that SHF? That solution will be look like this for that expression 3. Okay, now check this. We are taking the solution as a sin kx plus b cos kx for the expression 3. Okay, now we are putting the boundary condition as follows. Why we are taking the boundary conditions? Because you see, the wave function psi must be the well behaved. What is the meaning of well behaved wave function? So this is the postulate of the quantum mechanics. Okay, now well behaved means the psi of x, that means the wave function of the particle and the first derivative, that means d psi dx must be single valued and continuous at every point of x, okay. So that means at every point of the one dimensional potential box along the x direction. Okay, so that is the thing. We are taking the boundary conditions as psi of x equals to 0, because you see, just look at this. Psi of x, here you see, x is equals to 0. That means psi of x, that means here x 0. That means psi of x 0, because outside the potential well, there will be no wave function here and here in this side also. There is no wave function. Okay, so that means there is no particle, no wave function. Psi of x is equals to 0 at x equals to 0 and x equals to L. Okay, and we are taking the boundary conditions and applying the boundary conditions here in expression 3. In expression 5. So if you put psi x0 at x equals to L, x0, that means sine 0 will give you 0. Okay, so that part will vanish and you will get b cos k into 0 is equals to 0. That means cos x will give you 0. That means cos 0 will give you 1. Okay, so b into 1. That means b equals to 0. If you put, that means we are putting psi x is equals to 0. So from here we are getting, b equals to 0. Okay, so we can write psi of x is equals to a sine kx, a sine kx. Okay, here this thing has been arrived for at equation 6. Okay, now if you put the another boundary conditions, that means psi of x is equals to 0 at x equals to L. That means you can write a sine k L is equals to 0. Okay, so if a sine k L equals to 0, you can write that k L is equals to n pi, where n equals to 1, 2, 3, etc. We are not taking n equals to 0 here. Why? We will discuss it later. Okay, so the wave function becomes psi x is equals to a sine n pi x by L, because k, if you put the value of k like n pi by L, you see n pi by L, then you can write that expression 8, a psi n x, because n is here, a n sine n pi x by L. Okay, so this is the wave function for the, that means expression 8 gives you the wave function for the particle in one-dimensional box. Now you see, in that slide, you see in the previous slide, here you see we have written that k is equals to root over 2me by h cut square. Okay, so that thing we are using here. You see, kn, because the n is the number. Okay, kn is equal to root over 2men by h cut square here. Okay, so k, what is k? Look here, k is n pi by L. Okay, so k is n pi by L. So from here we are getting the en value. If you put k is equals to n pi by L, so you can get, if you put the value of k n is equals to n pi by L, n pi by L. Okay, so if you put k equals to n pi by L, that means you can get pi square h cut square n square by 2ml square. Okay, so this is the energy. This is the energy of the particle in one-dimensional box, where n runs from, again I am saying, 1, 2, 3, 4, etc. but n not equals to 0 here. I should write here n not equals to 0. Okay, n not equals to 0. Okay, so this is the energy. Okay, now you see, just look at this. En is this. This is the En expression. Okay, and now we are taking En plus 1. En plus 1 means if En is that level, this is the En just above this. This is En plus 1. That means plus 1. This is the nth state, nth, and this is the n plus 1th, just above this. Okay, so now we are looking what is the difference between two successive energy levels. Okay, so to get this thing, we can write En plus 1 minus En is equals to pi square h cut square. This, that means this is the En plus 1. Just substitute n plus 1 n plus 1 here in place of n. Okay, and this is the En plus 1 state energy of the En plus 1 state, and this is the energy of the En state. Okay, so this is the difference between two successive energy levels. Okay, now come to the slide. Okay, so what we have got, that is this is the Enth energy, and also we have calculated this thing. Okay, now what we want to show you that if you put here n equals to 1, because n cannot be 0 here, as I said, if you put n equals to 1, okay, so if you put n equals to 1 here, that means the ground state energy. Okay, ground state energy, what is the value? Pi square h cut square by 2 ml square, because n1, if you put n2, 4 pi square h cut square by 2 ml square. If you put n3, 9 pi square h cut square by 2 ml square. Okay, if you put n4, 16 pi square h cut square by 2 ml square. Now I am saying what will be the difference between two successive energy levels. That means I am trying to say that suppose E1 means pi square h cut square by 2ml square. E2 4 pi square h cut square by 2ml square. E3 9 pi square h cut square by 2ml square. Now take the difference, E2 minus E1. Take the difference, E2 minus E1. How will be the value? 3 pi square h cut square by 2ml square. E3 minus E2, 5 pi square h cut square by 2ml square. That means the difference between two successive energy levels are going to be decreased if you are going far away from the ground to the nth state. That means you see the difference. See the difference. See the difference. Okay, so this is E2 minus E1. This is E3 minus E2. This is E4 minus E3. Okay, so this is the thing, how the difference between two successive energy levels are going to be decreased. Okay, now come to the wave function. Come to the how the wave function you can draw. How you can draw the wave functions for each value of n. Okay, now see, this is the wave function. Okay, a n sin n by x by n. Okay, for the particle in one dimensional box. Now you see, if you put say x equals to 0, you see, if I draw a line here, okay, that means you see, so that means I am giving you the wall of the potential box, and here the wall starts at the point x equals to 0 and ends at the point at x equals to l. Okay, now at every point, that means at x equals to 0, at the two points, I should say at the 2 points at x equals to 0 and x equals to l, there are nodes. Okay, you see, for that also. That means if you say this is the wave function for psi 1, that means when n equals to 1, this is for the wave functions for psi 1 x. Okay, because if you put in 1, that means a sine pi x by l, that means, and in psi 1, if you put x equals to 0, wave function 0, x equals to l will be cancelled and sine pi again give you the 0. So at For psi 1x, only these 2 points will give you the 0 value. That means the nodes. So the wave function will look like this. Okay, but at x equals to, but for n equals to 2, this is the wave function for psi 2x. At x equals to 0, it will be 0. At x equals to L, it will be L for psi 2 when n equals to 2. But you see this point at L equals to 2, L by 2, sorry, L by 2. At L by 2, if you put psi 2x is equals to a2 sine 2 pi x by L. If you put x equals to L by 2, that means L will cancel out and it will be your sine 2 pi, sorry, say sine pi, L by 2 and L by 2 of L by 2, and here this is 2, so 2 will cancel out. Okay, sine pi, okay, sine pi will give you again 0. Okay, that means this is the another node here. That means at psi 2x, for the function wave function psi 2x, there are 3 nodes at equals to 0, L by 2 and x equals to L. Okay, and here you just see this is the wave function for psi 3x. Okay, here you see at x equals to 0, here x equals to 3, L by 3, and here x equals to 2L by 3 and x equals to L. Okay, so at this point, and this point, that means 1, 2, 3 and 4. There are 4 nodes at for psi 3x. Okay, that means number of nodes are going to be increased. Okay, that means for n equals to 1, there are 2 nodes, n equals to 2, there are 3 nodes, n equals to 3, there are 4 nodes. Okay, so when you are going to be in nth state, there will be n plus 1th node. Okay, so in this way, the number of nodes are gradually increasing. Okay, now probability density, that part. See, just here, the quantum mechanical probability density. Probability density means the probability to find the particle within the box. That means within, suppose this is the well in our case. Here x equals to 0 at that point, and at that point x equals to L. So we are trying to find out the particle inside the box. Okay, that means here inside the box. What is the probability to find the particle inside the box? That means x equals to 0, x equals to L. So this is the thing. That means P of x probability can be written as psi star x psi of x. Okay, that means we know psi of x is equals to an sin n pi x by n. So when you are getting the probability, that means psi star, that means complex conjugate is coming here. That means psi star can be written as psi star x is written as a n star, okay, sin n pi x by n. Okay, so in this way psi star can be written. Okay, now when you are taking that probability, that means psi star psi, that means it can be written, it is written as, okay, mod of psi whole square. Okay, that has the meaning psi star psi. Okay, so it can be written as a n square sin square, okay, n pi x by n. Now come to that point. When you are getting the probability density, okay, so all the wave functions which has the negative lobe, that means for this it is okay. So when you are getting that, so for that thing, psi 1 x mod square, okay, this is the thing. For this, psi 2 x mod square, okay. For this, psi 3 x mod. That means there will be no negative part. You see, this slope is in positive, okay, this slope is in negative, but when you are calculating the probability density, so you have to show this is the positive part, again this is the positive part. Here positive part, again positive. So that negative part is coming the upward. Okay. Acha. Now, how to normalize the, before going to the normalization of the wave function, I must tell you that the value of the energy, this is the energy, that means this energy has some features. This is the eigenenergy. Obviously, this is the eigenenergy. Okay. And this energy is non-degenerate. You see, non-degenerate. Non-degenerate means if you have the value for E1, say that means pi square h cut square by 2 ml square, E2 4 pi square h cut square by 2 ml square. That means E1 and E2 will have the single value. Okay. No another E1 and E2 of the same value you will get. No, there will be none. That means E1, E2, E3, E4 all have the single value. No other state with that same energy you will get. Okay, that means, so this is a thing. That means I must tell you that this is discrete. That means 1, 2, 3, 4, etc. value of n. You can put it here. This is discrete and non-degenerate. Okay. So when we will talk about the three-dimensional box, it will be better to understand. Now, how to normalize the wave function for the particle in one-dimensional box? Why we are going to this? Why we are doing this normalization? Because we know that our wave function will be look like this: an sin n pi x by l. So an is any arbitrary constant here. So we should want to get the value, particular value. How is the value? So this is the formulation of the normalization. Because you see why we are taking the this limit, because you see in our case this is the potential. Here we have started from x equals to 0 and x equals to L. Okay, this and this. Okay, this point and this point. Okay, now for this thing, you see we are getting the lower limit of x is 0 and upper limit of x is L. Okay, so psi star x, that means psi star psi will be 1. This is the formula of normalization. That means there will be 100% probability. What is 1? 1 means that is there is 100% probability to get the particle within this well. That means from 0 to L. Okay, that is why 1. That means 100%. 1. Okay, so if you just go through that integration, this is a simple integration. You know in class 12. Okay, so this is a simple integration, and if you put the limit, okay, you can get the value of that constant in, as I have told you that we should know that what is the constant, root over 2 pi L. So here comes out that thing. Okay, that means we can now write the normalized wave function for the particle in one-dimensional box is root over 2 pi L sin n pi x by L. Okay, that means we have got the eigen energy and the normalized wave function. The features of the eigen energy is non-degenerate and they are discrete, and the difference between two successive energy levels is going to be decreased is going to be increased. The difference between two successive energy levels is going to be increased when the n is increasing. Okay, so there are three features of the energy values of particle in one-dimensional box, and this is the normalized wave function where the normalization constant is root over 2 by L. Okay, normalization constant is root over 2 by L sine n by x by L. Okay, that means this is the eigen function of the particle in one dimensional box, and the eigen energy is this n square pi square 8 cut square by 2 m square. This is the eigen function. We can write eigen function, and this is the eigen energy. Okay, so this is all about for a particle in one-dimensional box. Now come to that part, the particle in three-dimensional box. Three-dimensional means we can draw this. This is x, this is y, and this is z. That means this. Where we have seen just before that what we have passed, that there we have used only one dimensional. That means this. This here we have used only the x direction. X equals to L here and here. But here we are using the three dimensional as x, y, and z. Okay. Now we are taking. Just before that, we have used the only one dimensional where we have used the only x direction, but here we are taking the x, y, and z coordinate system. That is why it is called the three-dimensional box. Okay, so I have just put it here only the eigen value of energy. Okay, and after that, we have put here only the eigenvalue of energy and the wave function. Okay, so I have here similarly I have used that nabla square psi of r. Here r means here x, y, and z coordinate system we have used. That means x here. That means x here x, comma y, comma z. Okay, nabla square. You know that is nabla. Okay, r means x, y, and z, the three-dimensional figure here. Okay, so the normalized wave function is coming like this. Okay, similar pattern, but here you have to use x, y, z three coordinates. Okay, I have only write the normalized wave function. That means the eigen function of the particle in three-dimensional box here, and this is the eigen value of the energy for a particle in three-dimensional box. Okay. Now here nx is 1, 2, 3, 4, etc. ny is 1, 2, 3, 4, etc. and z is similar. Okay. Now the interesting thing I should say that here if you see that figure, this is the cubic box. Okay. If you think about the cubic box, that means here the x length of the x coordinate, that means here to here, and length of the y coordinate here to here, and the length of the z coordinate here to here. The length, all the three lengths are same. Okay. Now just think about say L. Okay, x1 is equals to y1 is equals to z1. That is the L. Okay, that is the L. Okay, so if you put it here, that means you will get that type of value for the eigen energy in three-dimensional box. Mind it. Okay, if you put n1, one thing is that I should write in y here. N1 and nz. Okay, here will be nx. This is my mistake. Nx, ny, and nz. Okay, if you put E111, that means nx1, ny1, and z1. So what will be the value? You are getting 3h square by 8ml square. If you put 1, 1, 2, that means 6h square by 8ml square. If you 1, 1, 2, if you just give the combination of the quantum numbers, that means in x, n, y and z are the quantum numbers along x, y and z direction. Okay. One thing is that n, y and z. That is my mistake. I should write it here. That is in z. Okay. That is in z. Okay, and that is also in z. Okay. Okay. So if you put if you give a combination of 1, 1, 2, that means you can write 1, 1, 2. You can write 1, 2, 1. You can write 2, 1, 1. That means for all these states, that means all these three states, you will get the similar energy. That means the energy value will be 6h square by 8ml square. Okay. So that means you are getting a similar energy, but you are getting three energy states accordingly. Okay. That means threefold. We are saying it that it is threefold degeneracy. Now come to that point. Suppose again if you are taking 2, 2, 1. Okay. 2, 2. If you give a combination of that quantum number 2, 2, 1. 2, 1, 2, 1, 2, 2. You will get again the threefold degeneracy. That means okay. Now if you go for say 1, 2, 3, 1, 2, 3, if you go for say E 1, 2, 3. Take that example also. E1, 2, 3. That means you can, if you give a combination of the quantum states, that is 1, 2, 3. Okay, 1, 3, 2. Okay, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. That means how much degeneracy you have got? 1, 2, 3, 4, 5, 6. Okay, that means it will give you the sixfold. It will give you the sixfold. For that example, you will get the sixfold. Okay, so now look at this wave function. We are taking the, suppose just look like this. Look this. Okay, E112. Okay, if you take that 112 combination, that means if you put it here 1 NX1, 1 NY1, NZ1. Now just go for the another combination. Suppose 1, 2, 1, 1, 2, 1. That means you see what is my aim. That is, though you are getting the degeneracy of that combinations 1, 1, 2, threefold degeneracy of the energy, but the wave function is, you see, the wave functions is different for each cases. For each cases, that means you see, for 1, 1, 2, the wave function, whatever be the wave function, for 1, 2, 1, the wave function is different. For 2, 1, 1, wave function is again different. Okay, that means for these three energy states, the wave functions are different, but the energy values will be same. This is called the degeneracy. And since you are getting the three energy states of similar energy, okay, with different wave functions, this is called the threefold degeneracy. Here also similar sixfold degeneracy. That means there will be the same energy of 6 energy states, but 6 wave functions must be different. That is why it is called the sixfold degeneracy. Okay. One thing I have told you that why we are not using n equals to 0 here for the particle in one dimensional box. Here we are not using n equals to 0 because you see, just look at this wave function. Our wave function was this. You see, a sin n x is equals to a n sin n by x by n for one dimensional. If you put n equals to 0 here, that means a sin 0, that means the wave function, there will be no wave function for n equals to 0. Okay, that means if there has no wave function, that it has no meaning. Okay, that means you cannot do the application actually. Okay, that means you cannot take n equals to 0. That means it has no function, means no particle. It cannot be now. That is why we have started n value from n equals to 1, 2, 3, etc. Okay, that means we are not taking any 0. Okay, so for today we have stopped here. Okay, so thank you.